The following functions satisfy the hypothesis of the mean value theorem on the given intervals. Explain. So we know that for the mean value theorem, the function should satisfy two conditions. First, the function is continuous on the closed interval. That means function is continuous everywhere and at the endpoints. At the same time, the function is differentiable on the open interval. We don't care about the endpoints, but inside AB, the function should be differentiable. Okay? If one of these two conditions fails, or both fail, then obviously mean value theorem does not apply. So let's look at those things here. So in part A, we got a function x square minus 1 all over x minus 1, and we are looking inside 0, 2. This is a rational function, and domain is all reals except 1, because 1 minus 1 is 0, and something divided by 0 is undefined. So this function is continuous everywhere except at 1. And unfortunately, 1 is inside 0, 2. That means this function is not continuous here, because at 1 we are dividing by 0. So no. Now MVT, the MVT, mean value theorem, does not apply. Why? Because f is not continuous. At 1, that is inside here, we can just say not continuous on 0, 2. Okay, that's part A. Let's go for B, part B. So we got the function fx equals absolute x negative 1 to 1. And we know that the graph of absolute value of x is just a V-shaped graph. So this is the graph of y equals absolute value of x. And we know that at 0, we got a corner point. So this function is not differentiable. This is continuous everywhere, but not differentiable at 0. And it's differentiable everywhere else. So the function negative 1 to 1, so we are looking at negative 1 to 1. So clearly at 0, this function is not differentiable, which is inside this. So the mean value theorem does not apply to this function inside this interval. Does not apply on negative 1 to 1 because the function is not differentiable at 0, having a corner point, because the function is not differentiable. It's continuous though. Is not differentiable inside negative 1, 1. In fact, it's not differentiable at 0, which is inside negative 1 and 1. Okay, so let's look at C. So we got a function 1 over x minus 1. Looking at this function, we can clearly see the trouble point is 1, because 1 minus 1 is 0 and 1 over 0 is undefined. And we are looking at 2 to 4. Oh, the only trouble point here is 1, which is not inside 2, 4. So being a rational function, it's continuous and differentiable everywhere in its domain. So the domain of this function is all reals except 1. And this one is in domain. Okay, 1 is not inside 2, 4. So this is good. The mean value theorem applies to this function f because f satisfies both conditions. F is continuous on 2, 4 and f is differentiable on open interval 2, 4. Okay, let's go for D. So we got natural log of x. By the way, if you want to graph natural log of x, something like this, it's undefined at 0. Oh, we are looking at -1 to 2. So -1 to 2. Okay, natural log of x has a vertical asymptote at x equals 0. So natural log of 0 is undefined, by the way. And 0 is here, 0 is inside. So clearly this function is not even defined. That means the function is not continuous here. Okay, so we can write no. Okay, let me use the same color. No, the mean value theorem does not apply to this function f, as the function is not even defined. So it's not continuous, it's not even defined. Is not continuous and not differentiable, not continuous at 0, which is inside here. So not continuous on -1 to 2. Okay, and the last problem is f equals square root of x. So here, if we graph square root of x, that is something like this. So at 0 it's good, but we are looking from -1 to 1. Okay, and the square root of negative numbers are not defined. So like D, the mean value theorem does not apply because the function is not even defined, is not continuous. So it's the same like D. Okay, no, the mean value theorem does not apply to this function, to f, as the function is not even defined, is not continuous on -1 to 1. Final.